Hello, this is Mrs. Pullen, lesson 9.03 on graphing exponential functions. For the first problem, we're asked to sketch the graphs of f of x is equal to 2 raised to the power of x and g of x is equal to 1/2 raised to the power of x. Both of these are considered exponential functions, and we know that because we have a number for the base and a variable x for the exponent. So we can use any values to input for x, but we're going to use what's shown in the table from -3 to 3. So 2 raised to the -3 is the same thing as 1 over 2 to the 3. 2 to the 3 is 1/8. 2 to the -2 is the same thing as 1 over 2 squared, which is 1 over 4. 2 to the -1 is equal to 1 over 2 to the first, which is 1/2. 2 to the 0, anything raised to the power of 0 is 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. And so we're going to graph our function. I'm going to have each box as equal to 1 on the y-axis, and each box equal to 1 on the x-axis. -3, 1/8 close to 0.1 is 1.25. 1/4 is 0.25. 1/2 is 0.5. 0, 1, 1, 2, 2, 4, and 3, 8. And we make a nice smooth curve. We put an arrow on each end because there actually it actually goes infinitely far in both directions. Notice this curve is not crossing the x-axis, and we'll talk about that in a little bit. We have to label our function. Y is equal, rather it's f of x is equal to 2 raised to the power of x. So I want you to put the video on hold, and I'd like you to fill in the table for 1/2 raised to the x. Did you match me? Great job. So now let's graph 1/2 raised to the x, and so that is going to be -3, 8, 2, 4, 1, 2, or rather -1, 2, 0, 1, and then it's going to be 1, 1/2, 2 1/4, and 3 and 0.125. Again, we're going to make a nice smooth curve with the arrows on both ends because we don't have a defined interval, and it goes infinitely far in both directions. And please make sure to label. Please take a look at both graphs, and do you notice something about it? Put the video on hold and think about it. So if you said that g of x is a reflection of f of x over the y-axis, you are absolutely correct. Okay, so before we continue, let's go over some characteristics of the graph. So I'm going to put this graph on dual page. And let's go over some properties. First of all, the base has to be greater than 0. You can't have a negative number for the base. Also, the base cannot equal 1 because if suppose it was, you would have y equals 1 raised to the x, which would only be 1. It would be a constant line, so it can't be that. The natural domain for all exponential functions in the form y equals bx is x is an element of the reals, and the natural range when you have an exponential function in the form y equals b raised to the x is any number greater than 0. Both of these functions will never cross the x-axis unless there's a vertical shift. There's no x-intercept, and also all exponential functions are going to pass through the point 0, 1, the y-intercept, again, unless there's a vertical shift. exponential functions lie in quadrant 1 and quadrant 2. And actually, since exponential functions don't cross the x-axis, we say that the x-axis is an asymptote. And the equation of this is going to be the horizontal line, y equals 0. Again, if there's a vertical shift, it would be brought up or down the asymptote depending on the shift. On problem number 2, we're asked to graph the function y equals e raised to the x. E is actually not a letter. It represents an irrational number, and we call it the natural base. It's used a lot in science and in business. E is approximately 2.718, blah, blah, blah. It goes on forever, and it's an irrational number. And we're asked to graph this in the interval from -2 to 2. So we're going to go into our graphing calculator right now. And I want you to open up a new graph page. So you can either go to a new document, add a graph page, or go to the icon and add a graph page. So where is the base? If you look on the keypad on the same row as 1, 2, 3, there is the national base E towards the left. So you would just type in e raised to the x and hit enter, and hit Control T to get your table. And we're going to just adjust the table so we can see all the values. Whoop. I'd like you to record that on your page, so put the video on hold. So did you match the values in my table? Great. So let's go ahead and start graphing this. So we have -2 and 0.135, and -1 and 0.368, 0, 1, 1 and 2.738, 2 and almost 8. And again, we're going to label. And in this case, we don't put arrows over at the end of the graph because they defined our interval. So let's go on to the next page. So we're going to define terms called exponential growth and exponential decay. So when your base is greater than 1, we say that as x increases, our y values are going to increase exponentially. So an example would be 4 raised to the power of x. And if our base is between 0 and 1, then our exponential graph exhibits exponential decay. As x increases, our y values are going to decrease exponentially. An example would be 1/4 raised to the power of x. So for the following exponential graphs, I'd like you to label them as to whether they're exponential growth or exponential decay. So please put the video on hold. So for problem number 1, our base is greater than 1, so therefore this would be exponential growth. For problem part B, point 2 is between 0 and 1, so the exponential growth, the exponential function would show as decay. For part C, we can rewrite that function as 3/2 as 1.5 raised to the power of x, so our base is greater than 1, and that's why it would be growth. And for part D, I could rewrite the function as y is equal to 2 raised to the -1 to the power of x, or 1/2 raised to the power of x. So notice, once it's in the form y equals b raised to the x, we can see that the function decays. Put the video on hold and try example 4, which is from the June 2016 Regents number 15. Did you get choice 4 as your answer? If so, good job. If not, let's go over each part. So for choice 1, what you would do is first take that function and put it into y equals b raised to the x form. So in your calculator, type in 2 raised to the power of 0.3, and you can rewrite that other function as y equals 1.231, or approximately, raised to the power of t. So you can see that that would be growth. For part 2, you would do the same thing. And this is going to be a common theme that we're going to be doing throughout the rest of this unit. So we're going to rewrite these functions in the form of b raised to the x. So if I enter 1.2 raised to the power of 3, you get 1.728 raised to the power of t. Now let's do choice 3. So I'm just going to convert that to 0.5 raised to the negative 1 and bringing that negative 1 on the inside. So the function becomes 0.5 raised to the negative 1, and I get 2 raised to the power of t. And now let's do the last choice. We're going to bring that negative 1 inside. So now we can rewrite the base as 5 caret negative 1, or 1/5, which as a decimal is 0.2. So now we can see that that base is between 0 and 1, and therefore we can define it as decay. So for the last problem, this is from the June 2017 Regents, problem number 29. We're going to graph this function, okay? So they like providing this type of question on the Regents, and they'll ask other parts that we'll address in the logarithmic unit. So let's go to a calculator page. Again, you should always start a new document, or you can use the icon. And we're going to enter the function into the calculator as you see it. When I enter the function, however, I don't see anything. And the reason is that I need to readjust our window. So let's take a look. So when you're readjusting the window, you're really changing x min, x max, y min, and y max. And so for now, I'm going to keep the x min and x max as the default, -10 to 10. But the y min, I really couldn't see anything. But if I plug 0 into this function, 0.85 raised to the power of 0 is 1, and 1 times 400 would be 400. So I know that it's going to be going up to at least 400, and then we're subtracting 6. So I'm going to say that let's estimate the minimum value being 600. It may be smaller, but we can start off that way. And for the minimum value, I'm just going to go -100. I know the function is just going to be, there's a shift of -6, so it's not going to be really below -6, but let's try this out. So what you're going to do is you're going to hit Menu, Option 4 for Windows, and Option 1 for Settings. I'm going to keep X min and X max the same, but I'm going to convert Y min to -100, and I said Y max to 600. And let's see if I can see the whole picture. That's much better. In fact, I really don't need to see the graph prior to, I could minimize the x min to -4. Let's try that, just so it's easier for me to see. But you don't really need to do that. That's up to you. So I'm just going to make mine -4 and enter. And now I get a nice graph. So now we're going to hit Control T. And that enables us to go ahead and get the table so we can graph the function. So I want you to put the video on hold and record the values, and then we can graph it. So did you match my numbers? Take a close look. Okay, and now we can start graphing. We can see on our x-axis that every 2 boxes represents 1 unit, and on our y-axis, every 5 boxes represents 100. So again, put your video on hold and spend some time graphing. Make sure that everything is properly labeled. If this was a real-life problem, you would have to make sure to label the x and y axis with whatever information they gave. Have a great day.